All right, our next presentation is going to be coming from Robert Henschel from Indiana University. He's going to be talking about high-performance desktops for research.
As Brian said, this is all about AI, so let's start with this being interactive. Is this an AI-generated image, yes or no? The answer is no. It is the original marketing image that Cray used to sell their first version of the desk-side supercomputer in 2008, the CX-1, which, believe it or not, is actually a blade architecture, which also included active noise cancellation, because you were supposed to put that onto your desk. They sold that from 2008 to 2012 with a number of different blades. This is not what I want to talk about. I don't want to create the horror of all IT departments of more desktops out there that need to be maintained, and specifically expensive ones. I want to talk about different HPC desktops. So I want to first give you some context on my view of the HPC landscape, both from an infrastructure and from a user point of view. Then talk about the HPC desktops at the end. And there's not going to be a demo. Even if I had started on time, there would be no demo, because I have to 150 slides to get through. So let's do that. I thought let's put the goal out there so everybody knows what the goal of this presentation is. Goal is to first make you aware of HPC desktops for the people in the room who are not familiar with those, and then maybe get yourself to think a little bit about what it would take to create one in your organization and hopefully delight your users by having those. I've worked in HPC for almost 20 years now. I've been 17 years at Indiana University, all of the time in a user-facing role. Different roles, but always with the goal of getting more users onto the HPC machines, getting not just more users, but more diverse users from different fields of science. IU is a little unique in that sense that from the beginning, IU makes the machines available free of charge and without an allocation process to a lot of users. So IU has sort of seen the future when it comes to diversity of HPC users, simply because the machines are made available to people from the mathematics department to computer science, biology. I'm now in a part-time role with the university, and I do some HPC consulting on the side. And I've done a lot of user interviews, both in industry and in higher education. And I see a lot of those new users in HPC. Of course, a lot of them come from AI, because I think AI really has helped HPC to be more relevant again. But I see those new users struggling a little bit with adopting specifically the high-end architecture in HPC. So this is the market that I'm familiar with, which is not the high-end science, right? This is not mission-driven HPC organizations that have well-coded Fortran codes, that have large code bases and have been running them for a couple of decades. But it's more the users that are new to HPC, that are now forced into HPC because of AI, because of larger data sets, and because of the size of HPC increasing. And then I saw that post by Andrew Jones, I think in either December or in January, which I thought was really relevant to how I think about HPC. I think about HPC as increasing the productivity of the user, which ideally, right, the machines are effectively used, but in the end, the scientific throughput is the thing that counts. So let me talk a little bit about the state of HPC as I see it. I think more and more HPC cycles are becoming available. HPC machines are getting larger. You get to them in different ways now. You don't have to have them on-prem anymore. You can create smaller or even larger HPC machines in the cloud, which gets more users onto those machines. And particularly, a single node becomes much larger. I was very excited at the beginning of the 2000s when I got onto an SGI Altix that had a single system image for 1,024 cores and a terabyte of memory. Make-J goes really fast on those machines. Nowadays, you don't need to spend millions of dollars to get to a single node that has 256 real cores, and then you turn hyperthreading on. So those simple nodes can then run things like MATLAB or RStudio really fast, as long as they can take advantage of the parallelism in a single node. With those larger node sizes, you also get new users and you get new applications. Applications that in the past couldn't take advantage of HPC machines because they can't take advantage of distributed nodes, and for users running across nodes becomes hard. With those new users, you get a different skill set. And then the HPC infrastructure, I think, has very nicely adapted to this over time with things like Open on Demand, with things like science gateways. And as you see, this chart is not balanced, so I balanced the chart out by adding the HPC desktop as yet another way how to help users take advantage of the HPC infrastructure. One thing that is maybe a little out there, but bear with me for attention for a minute or two here. When you look at how HPC machines were programmed in the past, you have Fortran, and I'm personally a big fan of the language, but it really forces you into this mindset of writing down the recipe of your code, edit, compile, run, edit, compile, debug, run, which I think for everyone in the audience here is not a real problem, right? We're sort of self-selected for this. This is the kind of way that we like to think about. This is the kind of how we write a recipe, we process it, we run it. I would argue that a lot of scientists have a hard time with this model. And this makes it unnecessarily hard for them to use the machines. Now, in the past, there was no way around this, right? Given the resources we had, given the performance of the machine, compiled languages were the way to go. And maybe even computer science in the 70s and 80s wasn't where interpreted languages are today. Now, if you compare this with how most science is done and how people live their life, it's mostly iterative, right? You try something, you iterate on it, and you do it all iteratively, one step after the other, which is much closer to what you see in Jupyter Notebooks today. I've worked with a group in our image analysis department out of the medical school. They had a Jupyter Notebook with 150 cells, but the notebook did everything. It took the images, it actually decomposed an MPEG-4 file into images, did the analysis, produced the report, and then even did the uncertainty quantification on it in a single notebook. And they were very happy about the fact that they could run certain parts of this code until it finished and they went on to the next one. So I think moving into some of the more easier to use tools like MATLAB, like RStudio, like Jupyter Notebook is something that will draw more users into the system, and then you have to figure out how to run those on an HPC machine. The other thing with specifically younger people is, in the past, everything is file-based. Again, for the people in the room, that's not a problem. We've all grown up on text mode operating systems. We all know what your current working directory is, and you all know where your input files go, where a binary is, and what an output file is. The concept of a current working directory is surprisingly hard to communicate to students nowadays. Because it's the cloud, right? You search for your files, they're all going to return. If you look at an architecture like a Jupyter Notebook, it's a document. The document can contain the input data set, the output data set, and the recipe. It's a single document. Is that the best architecture? I don't know. But it's certainly a step forward for drawing people into the system. And to be fair, the lower left-hand corner, this is Fortran in Visual Studio Code. So to sum this up, I think HPC systems are becoming more widely available. We see more users on them. Users come with a more diverse skill set. And then to some extent, the HPC centers are asked to support all those users. Which, going back to the introduction, is something that IU has done for a long time. And we've struggled with this, and we've developed some solutions around it. Allow me to do another tangent before I come to the desktops. I said in the keynote talk by Matt Rocklin at the High Performance Python for Science at Scale workshop at Supercomputing, and in Atlanta in November. And he gave an excellent talk. Matt Rocklin, for those who don't know him, is one of the inventors of Dask, the Python workflow system. And he spent some time reflecting on what he has learned working with users over the years. And I think all of those facts are not at all controversial, right? Users don't read documentation. I think we can all sign on to that. No matter how well your documentation is structured, no matter how often you point people to it or what format it is on. Users are annoyingly creative. You give them a tool, they figure out how to break it. You give them a tool, and they use it in the exact opposite way of you intend them to use it, and they are proud of it. Users use diverse tools. I always say, right, it wouldn't be research if we knew what the outcome was, then it would just be production. You want to support users with different tools. Those tools evolve over time, as do their needs evolve. And users have really no idea how computers work. Specifically, when you look at parallel computing, it's hard enough for people to understand how even serialized algorithms work, but once you look at the complexity of a modern HPC system with the middleware and the networks and the storage, even for trained professionals like us, it becomes very hard to really have an intuition for how an algorithm will perform in parallel. And not knowing how something performs both stops people from scaling, wanting to run larger because they're like, what if I break the system? But at the same time, it also makes them inefficient, right? They may not know how they misuse the system. So he came up with 5 lessons. First one, if you give users a tool, try to make this tool as familiar to them as possible. Don't be novel. Don't write new APIs. Right? Give users something that they are familiar with, and then they can evolve with this. Invite users to invent. When you give users a tool, go into it with the intention that they will misuse it, they will combine it with other tools. Have your mindset be tuned to this. Make it visual. People really love looking at stuff. I don't know if you have ever used Dask. You have this workflow visualizer that you can connect to as your computation runs, and it'll actually show you how the algorithm is broken down, how the domain is decomposed, and how it is run. Matt called this the most important part of Dask. Functionality is absolutely zero. There's nothing. It just visualizes the problem, gives the user something to look at, and then the user becomes more familiar with how this problem runs. And then as it scales, the user sees how the problem is distributed across the nodes, and it helps them both develop an intuition, but also helps them become less anxious about running at scale. Tell people about their usage is a very simple thing. Tell them immediately how much they use, because once they see how much they use and how different algorithms lead to different usage, they are much more likely to experiment. And the last one, he was specifically going on about CUDA here, is the more you can make something useful on a laptop or a departmental workstation, the more likely you are for those people to scale it and then use it in the HPC context. So if people have to start out in HPC because by default there's no Fortran compiler on your OS, oh, maybe that works, then they're not likely to start with Fortran. So, and I think the HPC ecosystem has evolved on various scales to support those users, right? When you look at things like EasyBuild or SPAC, those are tools to very easily allow users to install applications. You have Open on Demand as a great web-based solution to get to HPC systems, container support, portals. So I'm not saying that the HPC ecosystem hasn't evolved. I'm just saying here's another way to do it. So when I gave a 5-minute lightning talk at the Interactive and Urgent HPC workshop at Supercomputing in 22, I wrote down what the vision would be for such an HPC desktop. And I'll do a little bit of an interpretive reading here, because it is still the best definition that I've come up with. And what I would like for you is to basically have this form a picture in your head about this, right? What if you had access to a high-performance desktop from any endpoint device? Could be a Windows workstation, could be a Mac laptop, could be an iPad. What if this desktop allowed you to launch interactive graphical applications like MATLAB, Jupyter Notebook, or Studio, but also compose scientific workflows? You can run a shell script there. What if the desktop had enough performance to run the applications, at least in small counts, right? Run MATLAB without the parallel toolbox, or Studio by itself isn't all that parallel unless you exploit parallelism and R. But also provide tools to quickly manage and submit jobs from the same system, right? So if you can run MATLAB on the HPC desktop, you can run MATLAB on your compute node. And what if the desktop is available to you for months? Not just weeks, just months, right? You can come back to it, it's still there, you disconnect over the weekend, you come back on Monday, it's still there. Looks like a very compelling vision. And this is sort of what IU has built, and other universities have built. IU certainly was not the first one to build it, and a concept like this is in use at quite a number of universities. So with this, I thought let's go back to the lessons learned. And I mean, I wouldn't have put up the chart if it would be different, but an HPC desktop is very familiar to users because everybody comes from a macOS or Windows laptop. There's very few users who come from a Linux laptop. A desktop is very flexible. You can customize it, you can run shell scripts, you can install extensions. People can invent with it. It's visual, it's intrinsically visual. The desktop itself does not really tell users how much they use, so there's certainly a gap there that needs to be filled with utilities. And yeah, it's useful on a laptop. So with this, let's go into the actual HPC desktop story. As I said, IU has quite the history on making HPC open access to everyone on campus, faculty, students, and staff. And there's a few papers that we've published on this, one of the earlier ones from 2016, which was about our Cray machine with K20s, basically having a petaflop supercomputer as a campus resource. And then a few papers as early as 2019 for research computing desktop, the paper we published together with Purdue University. The QR code here goes to an interesting white paper that was put together by the interactive and urgent HPC community that puts on the workshops at ISC and SC. It's a 24 paper that was in the end published in IEEE size and is published by now, which sort of summarizes the overall interactive landscape, right? So it goes over things like open on demand, science gateways, workflows, how to make HPC systems useful in direct engineering support. So this is something that you can look at if you want to learn more about the overall interactive HPC landscape. This is some of the slides I will, some of the next couple of slides are sort of copied from the talk I gave last year at ISC in Hamburg, which was use case for high performance research desktops. This was a combined paper with Lund University, Sweden, and Denmark Technical University. Both universities have very, very similar HPC desktops as what Indiana University has. Denmark Technical University, for example, started with this in the early 2000s on the Sun-Ray architecture, where they gave people lightweight desktops on Sun-Rays and then moved into this architecture over time. The guiding principle for all of this is convenience over efficiency. And this is where it gets controversial, specifically in the HPC ecosystem. The point is not necessarily to promote inefficient use of the HPC system, but promote a convenient use of the desktop to draw people into the ecosystem. Because the more you can get people into the ecosystem first, and you can show them that an HPC system can actually really, not just because you have to for your science, but can really help you with data analysis and with the science that you do, the more eager people are to learn, right? I used to teach the introduction to HPC classes at IU, and I used to make the joke that you would lose half the room before the break when you talk to them about SSH, and then you would use the other half of the room after the break once you introduced Slurm. Because at that point it was really, really inconvenient to use. And a lot has been done over the last couple of years to make this better, but thinking a little bit about the convenience of the system is important. Specifically, if you have a backend system with HPC compute nodes or application servers that can support this desktop, you can then really tune the desktop for convenience and tune the HPC system for efficiency. One thing that I will show a few things down the road is something that really hasn't been explored much, which is what can you do to a desktop to really make it feel like an extension of an HPC system? And I collaborated with a user interface class at IU last year where I explained the concept of an HPC desktop to a bunch of students, and they came up with mock-ups of what would an ideal desktop look like, what would tools look like, and I think half the classes basically put a chatbot into Bash to help users write better shell scripts. But it's a really interesting field in UI research. I spent a couple of hours in the IU library then looking at some of the UI proceedings from conferences in the late 80s, early 90s, when people were talking about what should desktops look like, right? What is the concept of a trash can on a desktop? What is the concept of a folder on a desktop? And I think it would be super interesting to explore something like this. If you had a desktop that sits in front of an HPC machine, can you represent the batch system with desktop metaphors? Can you make it easy for people to run, for example, MATLAB on a compute node? So this is what the architecture looks like. This figure is taken from the paper. When you look at the location of those HPC desktop servers, they look very much like login nodes, right? So the idea is they run in front of the HPC systems with access to the same file systems, same software architecture as the HPC system. However, none of the limitations that login nodes typically have. So when you look at Hogwatch, you look at limitations of how long PIDs can run on login nodes, you want those ideally be removed. You can still run C groups on the desktop nodes to limit people when it comes to how many time slices on the CPU they can use, how much memory they can use. But you want to encourage users to actually do some computation on those devices. And then you can get to them from anywhere. To show some examples from what those desktops would look like, this is not rocket science, it's a remote Linux desktop, right? So this is not, this should look very familiar. This is the version that Indiana University runs. Here's the one from Denmark Technical University. They basically included the application in the menu. You can click on that and they run on compute nodes automatically. This is Lund University with ParaView open. And they also have their own tool that helps them submit jobs, visualizes the batch scheduler. National HPC Center in Chile, and the Purdue University desktop, and then one that looks really bare bones, which is NERSC. So what are those use cases? And I originally had, I think, like one slide per use case, because that was really the meat of the talk I gave at ISC. But we can make this a little shorter here. The use cases are basically centered on the convenience side. So look at file management. For example, it's really hard for users to get their head around the fact that you can run a command to do something with a file, like CP or MV, right? For new users, that's not a convenient way to deal with files, specifically for people nowadays that come from cloud storage architectures. The fact that you're running the desktop in the same environment as your HPC system, ideally with access to the same file system, you can all of a sudden use a graphical file manager to move files from a Lustre file system to GPFS, for example, or stage them from a project file system to Scratch. And yeah, I mean, file managers have not necessarily been designed to deal with terabytes and terabytes of files, so there are going to be some issues there. And yes, users are going to be ignorant of the fact that this new subdirectory you just created has 100,000 files in it, and copying them takes some time. But here you at least give people a chance to do this in a visual environment before they learn how to scale and write shell scripts to tar up directories. Also, the ability to, for example, right-click on a tar archive and pick unpack from the context menu, instead of having to type that in a command, specifically for new users, is really powerful. Then, as I said, on the convenience side, you want to allow people to do a small amount of computation on those nodes. You want them to run RStudio, you want them to run MATLAB. So anything that allows people to get work done that may initially not require an HPC system but can benefit from the same tools, right? If you install the computational tools for the HPC system anyway, and some of them come with graphical front ends, then allowing users to run those on the desktop will be a lot. A lot of users will benefit from the ability, for example, to just run MATLAB for a week or run RStudio for a couple of days to finish a computation without having to figure out how to put that into the batch system. The other thing is, if you want to run MATLAB and you want to run MATLAB scripts, do you really want to do this in a compute node when all you do is you're doing editing and you're doing testing, right? Is it the most efficient use of a compute node if you were sitting in front of the MATLAB GUI for 6 hours to write algorithms and debug stuff, if you could do that on a shared node that 20 other users are on? Anything related to HPC workflows is something that the desktop is really great at. You can use a syntax highlighting editor for your shell scripts. It's a graphical editor. You can copy things around quickly. It helps people get into this file-based notion of really understanding what your current working directory looks like if you can actually see that in the file browser before you run a job in that directory. Some things work really well. There's nice applications that actually have this client-server concept. For example, MATLAB with the parallel server, or COMSOL multiphysics, the Schrödinger toolbox, where you have a graphical application that will spawn jobs or will directly connect to a compute node. The fact that the HPC desktop runs so close to the compute nodes, you most of the time have no firewall between that desktop and the compute node. So there's direct IP connectivity. No need to build an SSH tunnel from your machine via the login node to a compute node. Yes, ChatGPT will write that syntax for the SSH command for you nowadays, which helps you not to Google it all the time, but it's a convenient environment if the client, the UI, can easily talk to the compute server in the parallel environment. HPC desktops work really well for classes, both when you want to teach HPC and if professors on campus have computational intensive applications that they want to use during classes. The other advantage here is it actually democratizes it a little bit because all the students have access to a powerful enough workstation that can run MATLAB without having to either go to a computer lab or have to have a powerful laptop to run it. So let me go back to the big picture on this. There is a number of, I've broken this down to things that work for users, things that work for the HPC center. So the ability for users to disconnect and reconnect to the same environment, for example, in an HPC class, right? If you teach HPC trainings and you do this on a desktop that at the end you just disconnect from, and when the students wants to redo the exercise another day, the desktop is still there. The shell is still open, the module environment is still loaded. So people can actually continue with work they do in class later. The same if you have some, I know how to use screen, and I forget about using screen all the time. And when I'm in an SSH shell and I have started a long-running rsync command, for example, it's always then when I'm like, man, I should have been in screen. Then disconnecting from the SSH shell is just not an option. The ability to do this on a desktop where you can disconnect from the environment while the shells on the desktop are still open is a very convenient experience. And as I said earlier, once you get people into the environment, they will learn. Right? They will learn how to use the system more efficient down the road. If you lose them on step one, which is getting them into the system, they will not learn because you've lost them on step one. Right? So the more we can do to grow the HPC user base, I think the better for all of us. And I think AI has done a lot of good things for HPC. Right? The fact that HPC architectures are really great for training AI and using it is fantastic. So I think we've stopped a little bit the decline of HPC in the niche. But still, I think the more HPC centers can do to provide services to more users, different fields of science, become useful for new fields of science that now have larger data sets that they didn't have in the past, I think the better for everyone. Specifically, if you can do this by leveraging the infrastructure that's already there, right? Creating a new desktop environment, but then leveraging the storage systems that are there, leveraging the network, leveraging the support documents is something that's pretty easy to do. And then here's the little dig on Open On Demand. I can't help. You can actually administer desktops with shell scripts. This does not require full stack web applications. This does not require running web servers. Administering Linux desktops, creating icons for users, manipulating menus can all be done with shell scripts. So that works really well for HPC system administrators. And just to make it very clear, my point is not that we shouldn't be using SSH going forward. The terminal is great, right? Once users grow into this, I think everybody's going to be more efficient with terminals. I'm also not saying that Open On Demand is a bad solution. I think the way you see Open On Demand adoption across the HPC landscape is great, and it certainly draws more users in. But at the same time, going back to what Matt Rockland said about, users are annoyingly creative. There's only so much you can do in a web-based environment. There's only so many applications you want to launch through a web-based user interface that become yet another tab in your browser. So if you're interested in following up with this, I can highly advertise the interactive and urgent HPC workshops, both at ISC and SC. The workshops have been accepted for this year's ISC and SC. The call for papers is done for ISC, but there will be one that comes out in a couple of months for supercomputing. So if you have topics that require interactive use or urgent use of HPC machines, that would be a good venue. I've also started to put together a GitHub repo to collect some of the best practices, some of the tools around HPC desktop. This is certainly a repository that will evolve over time, but that's something that has some videos already. If you're interested in following up on this, take a look at this. And then I have just enough time to talk a little bit about the desktop customization stuff. Who in the room is familiar with wipe coding? Okay, so get ready. So integrating desktops with HPC is something that is really hard to do for people like me, right? I can code. I wouldn't necessarily call myself a software engineer. The code is certainly not beautiful, and also takes me a lot of time. But exploring this was something that was really hard for me to do in the past because I couldn't justify spending days and days to figure out how to write a Qt5 application or write a GTK application that runs nicely on a Linux desktop. However, thanks to things like Cursor, GitHub Copilot, this is all very different nowadays. You can create and you can explore things really fast. So let me just have 2 slides on this. This is an application I put together in about 3-4 hours. It's basically Qt5 as the user interface toolkit with Python as the language. The application is smart enough to basically query Slurm for all the partitions that exist. It'll query the partitions for GPUs, and it'll make a nice little container with each partition being an icon. And then you work in this and you say, hey, I want to run an interactive job in that partition, and I want to use GNOME Terminal as the terminal adapter. And it'll add a context menu. You can click on it. You get a nice little interactive job UI. It'll already know what kind of things Slurm supports. It'll know the maximum, right? You can submit a job that will never run. And this way you can easily prototype the fact that you have an icon on the desktop, you right-click on it, you run an interactive job. As I've shown earlier, some HPC centers have put the applications that are running into the application menu in GNOME, if you're familiar with the window manager. So I went a little step forward and said, well, I want to run every application that we have in analytics through the batch system. So it'll parse the menu, it'll create the icon, and then you can run MATLAB by just right-clicking on any partition and submitting it. Now, will this job run immediately? Of course not, right? Your HPC centers, the queues are full. But that's one way to really think about new user interfaces. My personal favorite is I'm really a drag and drop person. That is probably a personal problem of mine, but in implementing this with the help of cursor is straightforward. Those things now become drop targets, and you can actually drag a shell script onto any one partition. And then the AI will write the proper code, the proper SBatch directives around it, and then a shell script that will run on your desktop to do something, you can easily run in batch. Or let's look at the desktop specifically, again, coming back to the file manager, because as much as we can grow compute, growing storage is great, but that just means people consume more storage, right? And then people need to clean up that storage, and people need to do data management on the storage. Which, doing this in a web interface and doing API calls back and forth to your file system may be one way to do it, but if you had an application platform like an HPC desktop where you can run a user interface that can, for example, look at your file system, you can show the number of files, you can show quota, but then you can do something with it, right? I created this application in, again, less than 6 hours where you can look at your quota on our machines, and then you can actually drill down directory by directory. And if you right-click on any one of those slices, you can either bring up a shell or the file browser in exactly that directory, right? So if you want users to help tar up directories, if you want to give users a tool to clean up directory, that would be one way to do it. So I guess the pitch here is the HPC desktop as a place to do vibe coding. All right, if you want a demo, either of those tools or of the desktop, find me in the break. Thanks to Brian for scheduling this talk early in the week. I'm here until Wednesday, so as colleagues from IU will tell you, I love nothing more than talking about research desktops and vibe coding lately. So if you don't know what to do in a break, find me. Brief summary, HPC desktops are a thing. There's a number of institutions out there that run those, specifically in the academic sector, specifically to draw more people into centralized infrastructure and leverage HPC for sciences that would normally have a hard time using it. If you're interested, let me advertise again the interactive and urgent HPC workshops, both at ISC and SC. And with this, thank you for your attention.
Thank you, Robert. Thanks for reminding us that personal supercomputers actually existed for a hot minute. Yeah. We have time for a question or two. Anyone have? Yes, sir.
I'm seeing, particularly the last 6 months, a sharp uptick in users just wanting to use their VS Code on their PC and connect it to the HPC systems. If you've ever had to support users doing the whole SSH Slurm dance, it's difficult. Have you looked into that? I mean, I don't know how, I think most of our users who want to use VS Code wouldn't really be in love with kind of going to a browser, starting a session, getting VS Code on the desktop and then using it there. They just want to use it running natively on their desktop. Have you looked at that way of doing things, like applications connecting directly?
So we allow people to run the VS Code server on the login nodes. So you can run the SSH, the remote development extension, I think is what it's called. We have users who want to, because they can connect to our login nodes, but the login nodes run hogwatch, right? So the VS Code server will get killed quite a bit. So we now have users that want to tunnel through the login node to a compute node to run the VS Code server. At which point you really have to wonder, is that the right place to run VS Code Server from how expensive
Yeah,
that
well-
equipment is, right? So we provide both Spider and VS Code on the research desktop. People can basically just double-click and run it right there. That's our current solution for VS Code support.
But we find that the tunneling is quite clunky once you have to go onto the compute node, and then also sometimes users don't want a whole compute node. You want to be able to give them a tiny slice.
And everything's a job, right? A job has a runtime. When was the last time that you knew how long you want to be coding?
Time for another question.
Just riff on that one a little bit. I'm Brian Vanis from Livermore, by the way. So one of the big problems we see is that many people don't know how long their job should run. They also don't know that many schedulers will allow for backfilling algorithms, where if you run shorter jobs for less amount of time, you can actually get things in the queue while big jobs are going to flush the entire, drain the entire queue and block the whole system. And so just thinking about ways to bring that to your sort of environment. Like there are some schedulers that will allow you to query the backfill algorithm and say, how much could I schedule for how much time and get it?
Yeah.
And working with people who are developing new schedulers and just existing ones, and then making that visually available would be really a good way to help people increase their efficacy in batch scheduling.
Yeah, so we had a visualization for this a couple of years ago in a web interface that would basically show once you gave the algorithm like a core count and a runtime, right, it would show where in the hole in the schedule it would fit. And you could play with this. I thought about recreating this visualization and just allowing people to basically draw a rectangle into the hole in the backfill algorithm, right? So that you can say, give me a shell script that fits this algorithm. And maybe in the afternoon today.
Okay, Robert Henschel, everyone. Thank you.